In this series of videos I'm attempting to repair and restore an HP9845B vintage computer. So far I've been through quite a lot of the system, found a few issues. I'm currently waiting for some replacement parts, and while I'm doing that I'm going through some of the other parts of the system, trying to figure out what the other faults are. I know there are quite a few faults on this machine, and the next thing I was looking at was the keyboard interface. Quite a simple interface, got a bit of an unusual interface IC, but that appears to be working. But what I noticed as I was trying to trace through the code in the PPU, it was getting constant input from the keyboard. It was like several keys were pressed down all the time. But I did check and none of the keys were actually down. So I started investigating the keyboard interface, and that seems to be doing what it's supposed to, except that this IC in the top corner is the it's the feedback, it's the return from the keyboard. So it's basically a scanning system. It's in the matrix, it scans, and then this IC detects any keys that are pressed, but it's been triggered all the time, so, and that on all channels apart from one. And it's not a faulty IC, it does seem to be doing what it's supposed to, but there is no output because it thinks the keys are down all the time, so the keys are never being released. And so I decided to pop the keyboard out. Most of the keys actually stick down if you press them, so I turned it over, and this is what I found. So as you can see, it's a bit on the grubby side, and like I say, if you press any keys down, the keys stay down. So what I need to do is get this cleaned up, dismantled, check all the keys. I have buzzed them out on the back, and most of them do appear to be shorted as if they're the keys pressed down. So I need to get this clean. It's not going to work as it is. If I unplug the keyboard, the ribbon cable from the keyboard, then all the signals going back through the keyboard interface stop. So it's definitely signals coming from the keyboard itself. So I'll get this cleaned up and see if I can make any progress. So that's how the keyboard looks after it's been cleaned. As you can see, a big improvement. Had a few problems with this. The first was that 3 of the keys are supposed to be latching keys. So when you press them down, they should stay down when you press them once, and then when you press them again they should release. So these 2 were sticking, but they freed up quite easily. But the last one is the caps lock key, and fortunately, as it turned out, I had to remove that to get it to work. And these keys, the way that they're designed, they're kind of destined to fail. There's a very small metal spring clip, and it rides inside like a dual channel groove, and that's what's used to control the toggling action of the key. And the way it's designed, it's just going to fail. There's no way around it, and luckily I was able to effectively change the profile of the little groove, and it's a bit of a fiddly thing to do, but it now does at least do what it's supposed to, and it toggles down and does what it should. It will stay down, press it again, it comes up. So I can refit that. But when I took this out, it obviously left a hole in the metal plate, so I could see through that. And although you can't see it, when I looked in there was a huge amount of kind of green salt type corrosion, and I think that's what was causing the conductive paths that were causing the issue that we were seeing, where it thought a lot of the keys were being held down. And that was after about 45 minutes in the ultrasonic bath. So I put it back in the bath for another probably hour and a quarter, ran it at about 40 degrees, took it out, rinsed it, put it back in for another half an hour, and now as I said, you probably can't see it, but now all the corrosion seems to have gone. So what I'm going to do now is get this plugged back in. I'm not going to refit the other key just yet. I'm going to get this plugged back in. It just plugs into the interface, and we'll see if we're now getting sensible signals out of the interface card. So I'll get this ready, and we'll have a look on the scope and see what this is now doing. I've got the interface card plugged back in. I've plugged the keyboard back into the card as well. Power up the machine. And what we'll do now is look at the output of the amplifier chip. Before, we weren't getting any sensible signals out of this. It wasn't toggling at all. I think it's because it thought all the keys were mashed down. Now, this is supposed to have N key rollover, but even so, the certain keys inhibit the interrupt mechanism. It stops it continually generating interrupts when certain keys are held down. And I think what was happening is the keyboard interface thought lots of keys were held down, and so it was inhibiting any further key action. But if I put the scope probe on here now, we are getting exactly what we should. So that's the signal that was missing before. So it looks like we are getting the proper operation of the interface. We'll just check some of the inputs, see how they look, and that is looking much better. Okay, the next thing I want to look at, let's turn this off. So the next thing I want to look at is the sounder. The sounder is used for indications in quite a few tests, so I'd like that to work. And the way this circuit works, it should be able to beep even if the two processors aren't running correctly, and it's not doing anything. Now, another speaker worked. I tested that while I had the keyboard out, but it's still not doing anything. Now, it is quite an interesting circuit that they've designed for the beeper sounder, and this is it. I don't know how well this comes across. As I said, some of the schematics aren't particularly clear, but what we've got here is a fairly simple circuit, but it's quite ingenious. The speaker's connected to this transistor, so if you supply an alternating signal to the base of the transistor through this small filter, you'll get a tone coming out of the speaker. So that signal is provided on this pin of this gate, and if the other two pins are both low, that signal will make it through and it will drive the transistor and you'll hear the tone. But the clever part is that they arrange this that you could either disable that tone by raising the level on this pin, or you could have it automatically time how long the tone lasted. And so this IC is actually a dual 4-bit counter, and the two counters are organized in series, so effectively it's an 8-bit counter. So the signal comes through, assuming this gate is enabled, that is, this pin is low. This is the 7th or bit 7 of the counter, so when you reset the counter, this pin goes low. Assuming this pin is also low, the signal comes through, you'll hear the tone, but this input to the counter is the clock input to the first of the two counters. So it will start counting, so it's counting the pulses that are generating the tone. And because this output is bit 7 of the counter, after 128 cycles of the tone, this pin will go high and it will effectively disable this gate. So it will, when you reset, you apply reset, these two pins are the reset for the two counters. So when you reset the two counters, this pin will go low, that enables the gate. Assuming the other pin is also low, the tone will start, and after 128 cycles, the pin controlling the gate will go high and it will stop the tone. So it's kind of a way of having a very simple mechanism without the processors needing to keep track of how long the beep has been going for. It's kind of a fire and forget thing. They just tell it to make a tone, and then after the preset amount of time it will automatically turn off, assuming it's enabled in the first place. But this is not working, and so it could be one of the other 4 signals is not doing what they should, but we'll start buzzing this out, see what we can find, and we'll start with this gate. So firstly, we're looking for a tone on the input to this. This is where the start is, if you like. If we're not getting anything here, we won't get a tone in the first place. So we need to look for the incoming tone, and that is pin 4 of U14, which I believe is the numbered 1, 2, 3, 4, 5. That's I think that's IC14. So we'll turn the machine back on and see if we're getting a signal on pin, did I say pin 4 of that IC. So we are getting something there. That's the tone that we should be seeing, and according to the scope it's 577 Hertz, so it's kind of a medium pitch tone that we should hear coming through the speaker. So that's working, we're definitely getting something there. So the next thing we need to look at is pin 3, see if the actual sounder is enabled. This should be low, and it is indeed low. So that gate is enabled as far as the first pin is concerned. We'll now check pin 5, that also needs to be low. So pin 5. Okay, that's interesting, that's neither one thing or the other, so it's not low, so definitely above the threshold, and that will mean that this gate is effectively disabled. Let's try pin 6 and make sure nothing is coming out, and sure enough it is low. So we need to go back and see where the signal from pin 5 is originating. So if we get the schematic, okay, you're not going to be able to see this, I shouldn't think, but it's coming from here. So we should be getting, okay, so that's the 7404, so it certainly shouldn't be showing what we're seeing on the scope, so I suspect that gate might be faulty. So we'll try and buzz that out. That is, let me see, that is this one. Okay, that's not looking right either. Okay, so it looks like we have an issue with this IC. It's going to turn the machine off. So it looks like we've got either a fault with this IC or a fault on the input to the other IC, the IC14. I don't think it's a problem with IC14 because the nature of the signal we're seeing coming out of this gate tends to indicate that it's pretty much open circuit. Normally, when you get a faulty 04, the outputs will generally be tied to V plus or 0 volts, but this is not. It looks like it's floating. So what I'm actually going to try and do is something I don't do very often. It's not something I really recommend, but I'm going to piggyback another device on top of this. I don't normally recommend it because if there is a short on the output, you can end up damaging the device you're using to test. But in this case, because I think it's open circuit, I think it should actually work okay. Okay, so I've got a replacement 7404. This actually has a HP part number on it, but I'm pretty sure it's a 7404. And looking at the schematic, it would seem to indicate that's what's called for there. So this is just, the pins are bent slightly in, so it's kind of pressing on the pins of the IC on the board. As I say, be careful if you do this sort of thing. It's not a good idea unless you're fairly certain that the device that's on the board is open circuit. I'm pretty sure this one is. So we'll power it up, scope it, and see if the signal's improved. Okay, that's interesting. Actually beeped that time. Try it again. Okay, well that's what we wanted to hear, is the beeper going off. So it's going to check the signal and see if it's improved. Okay, and so that's now looking much better. That's what we should be seeing. I'm just going to try pressing a few keys and see if we can get it to beep in response to a key press. Okay, well clearly it's working to a much greater degree than it was. So what I'm going to do now is take the board out. I'll remove the faulty IC. I'm going to put sockets in for any ICs that I replace, but that's a step forward. At least it means now the system, in theory at least, can start to identify its status and the results of any tests. So I'll get this IC replaced, we'll make sure it still works, and then we can go from there. So I've removed the device, and sure enough it tests as faulty. In an earlier video I mentioned that when I replace parts, especially on vintage machines like this, that I try to make the repairs look as factory as possible. One thing you can do when you are working on boards like this, and incidentally if you do work on these, be aware these are multi-layer boards, they're not just two-sided. Some of them are actually 6-layer, and you need to be really careful if you start desoldering components, because it's very easy to destroy the through-hole plating on old boards like this. And if you separate a connection from an inner layer, you end up having to put jumpers on, and it starts looking very messy. So just be aware of that, be very careful when you unsolder components off these old boards. But if you want to make these repairs look factory, then what you can do is, depending on the solder you're using, select a solder that has a similar cold appearance to what you're trying to replace. As solder ages, it tends to go fairly dull, and if you just use a modern solder with high flux, it will be very shiny and it will stand out. And also try to mimic the amount of solder that was put on originally. So this is the one that I've replaced. So hopefully you can see it looks very similar. It's slightly brighter than the others. I needed to get the solder slightly cooler, but by the time it's been on there for a week or so, it will be very similar to the solder on the rest of the devices. So you can make it look as if though you haven't touched the board. This is the one I've replaced. I put a socket in, so I get a new device fitted. We'll get the board reattached and see if our beep is still there. I've got the interface refitted, got a new 7404 plugged in. We'll power it up and see if we still have the beep. And we do. So try a few keys. So it's working as far as that's concerned, and in the next video we'll start looking at fault finding on a few of the other boards. But really all I'm going to do is follow this process through, start tracing through the code. I still need to get the ROM modules made up. I'm waiting for the boards to be delivered so I can make up a couple of those modules. Someone did point out, and it's probably worth mentioning, you can buy EPROMs that have latches on the address lines. They've been available for a long time, and they're really for designs where there are multiplex buses like we have here. But unfortunately the devices used on these HP machines were designed before the standardization of pinouts on things like EPROMs and RAM, so they don't fit into the sockets that we have. And also a 64K EPROM is generally 28 pins, so it won't fit into the space that we have. But if you wanted to, you could make up an adapter and use a 28 pin EPROM that has latches on the address lines. I'm not sure we'd have space for it here. It's actually very close. If you look at the spacing between these boards, you've only got about 2 millimeters from the tops of the packages to the underside of the pins on the adjacent boards. So making up an adapter that will fit in the space is going to be quite difficult, but you could probably do it if you tried hard enough. But I'll explain why I haven't gone down that route when we get to look at the replacement modules I'm making up. There are other benefits to the way I've gone about designing them that will make them far more useful for us. But we'll get onto that in a future video. In the meantime, while I'm waiting for those to turn up, I'll carry on working my way through the rest of the machine. Got quite a lot to look at yet. We've got the tape drives, the keyboard seems to be behaving itself, but I now need to test all the keys. Also, I said I put this in the ultrasonic bath. It's okay with this type of keyboard. This keyboard uses, if I have a look at the key I've taken out, you probably can't see it, but there is a reed switch, basically glass encapsulated magnetic switch in the center of the switch housing, and the plunger, you probably can't see it, but there are two magnets on this, and they are what are used to operate the switch. So all the contacts are completely enclosed, so this type of switch and keyboard, it is safe to immerse as long as you dry it out, and this has had about 36 hours to dry out in a nice warm oven. So just be aware of that. Don't put membrane keyboards into the ultrasonic bath. You'll have a real pain trying to dry them out, and that's if the membrane doesn't separate in the liquid. But this type of keyboard, it's safe to do that. Okay, so as I said, in the next video we'll carry on with the fault finding, work our way through the various circuits, and try and get more and more of it working. But I suspect we're going to see more of the same sort of thing, where certain devices have started to fail, and they might work to a certain extent, but I've got a feeling we're going to see a lot of just poor quality signals that we need to deal with.